I'm Alex.
I'm Ryan.
And we're doing guitars.
Go ahead.
Thank God for calculus. Leibniz and Newton gave life meaning. To explain engineering and economics, and why the chicken crossed the road. Find the line tangent to the instantaneous rate of the function and its equal straight. Oh, it's all calculus. Never forget your plus C with your grade. We'll use Rayleigh sums to integrate. All I want is the area under the curve. Oh my, calculus. 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 Give me a 5 on the AP test. 'Cause lately I've been studying oh so hard. Kruger's retired, but he still really cares. Maybe he cares more than me. Find the line tangent to the curve, the instantaneous rate of the function at x equals 3. But what about the integral? Oh, it's all calculus. Never forgetting your plus C with your grade. We'll use Rayleigh sums to integrate. All I want is the area under the curve. Oh my, calculus. 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 Oh my, give me calculus. Oh my, I'm calculus. Oh my, I love calculus. Oh my, drive this with the product rule, the product rule, the product rule. Drive this with the product rule, the product rule, the product rule. Help me God with the product rule, the product rule, the product rule. Help me God with the product rule, the product rule, the product rule. It's as easy as f times g prime plus g times f prime. F times g prime plus g times f prime. Easy as f times g prime plus g times f prime. Easy as f times g prime plus g times f prime. But what about the quotient rule, the quotient rule, the quotient rule?
Wait, can't we just bring the denominator up top and then we could use the product rule?
So you're saying we don't even need the quotient rule, we could just put the power to the negative first, throw it in the numerator, and just use the product rule, 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 the product rule. Thank God for the product rule, the product rule, the product rule. Thank God for the product rule, the product rule, the product rule. My, calculus. 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 Of all the problems that e'er I done, I've struggled the most with this one. And all the rules that e'er I've learned, this seems the most useless to me. And
And all I've done for 9 long months is study for that AP test.
Now I've taken that, and I'll surely pass. Good luck to you, don't get a 2.
Of all the teachers that e'er I had, you're the one who won't give up on me.
And all the classmates that e'er I've had, you're the ones most likely to get a 3.
But if by chance it does happen that I should pass, and you shall not,
I'll gently rise and I'll softly call, no college credit for you all.
all right. Well, wasn't that great? Well, we obviously chose guitars. I think we said that, but we chose guitars because guitars are awesome.
They are indeed.
But yeah, on top of that, both of us have been playing guitars for like combined almost 15 years.
14 of those years have been Ryan, so
Yeah. Regardless, it's still pretty impressive. Yeah. Well, we love playing guitars, and even more than that, we love sharing our music. That's kind of evident, and we're both kind of involved with our church bands. So we love to give other people music,
I'd say I love music more than life myself.
pretty much.
Yeah.
Yeah. And I have shout out to the love of my life for making me so passionate about guitar, Taylor. She's a beauty.
I'd like to throw a shout out to Mumford and Sons, because they're pretty cool. You should listen to them sometime. So that's why we chose guitars.
Yeah. Okay. Now we have a little bit on the history of guitars. At least stringed instruments can date back at least 4,000 years. There are hieroglyphics and depictions of like stringed instruments such as harps and timbres. Timbres is what we see there, dating back to at least 2000 BC. And it should also be noted that the word guitar originates from Sanskrit, the word tar meaning strings. If you don't know much about Sanskrit, it's an ancient dead language, so that can kind of show you how old this is. And finally, the modern guitar kind of came out during the Renaissance era. Before this, guitars were all over, and they didn't really have it standardized. They were commonly using 4 or 5 strings, but during this time, they kind of standardized it to 6 strings with the now standard tuning of E, A, D, G, B, E. And then later much later, a couple hundred years, they started coming out with varieties of guitars. Like in 1850, the Spanish dude, Antonio Torres, finalized the classical guitar, which is this one, as you see. It's a lot like the modern acoustic guitar, except it has a thicker neck and it uses nylon strings. So it's a lot more for the finger-picking styles. Steel guitars were invented in 1900 by Frederick Martin. It's kind of cool. This guy, he actually got the Martin Guitar Company named after him. So he was kind of influential. The steel guitar is basically what it sounds like. It's a steel guitar. And he standardized the use of steel strings as compared to nylon or other types of strings. And the electric guitar emerged in like the roaring 20s with the invention of pickups, which like a microphone for a guitar. And with these pickups, we could now use solid body guitars where we didn't need the inside of the guitar, the body of the guitar to resonate the sound. So
sound brings us to waves, obviously. And so the height of a wave here, also known as the amplitude, is directly proportional to the loudness, so it directly affects how loud it is. So a small amplitude wave, such as this, is very quiet, and a large amplitude would be louder. And so that brings us to wavelength, which is the distance between 2 waves, the distance between the crests of the wave. And so that also, the time between there is the period, and that brings us into frequency.
and frequency is the number of periods per second. So it's the number of times the wave repeats per second. That's measured in hertz. A human can hear between 64 and 23,000 hertz.
Hello, Mr. Kruger?
Yes? Yes?
Hello, Mr. Kruger?
Yes? Hello? Yep. You okay? Sorry about that.
So the human can hear between 64 and 23,000 hertz. So 64 hertz being a very low note and 23,000 being a very high note. And different frequencies will emit different pitches. So a low frequency is a low pitch, high frequency is a high pitch. And kind of the history of waves here, Pythagoras, who lived in the 1st century, discovered that vibrations is what caused sound. And he also discovered that as the air vibrated, that is what transferred the vibration of the sound. And he also made the discovery that the length of the string is relative to the pitch, so the longer the string you have, the lower the pitch, and vice versa. Martin Mersenne made his important discovery in 1637, and he made Mersenne's rules on strings, which directly related tension, weight, and length to the pitch of the note. And then Heinrich Hertz in 1886, he was the first person to map waves, so he was the first person to see what a wave actually looks like. And he realized that all waves were kind of a translation and an adaptation of the sine function. And because of his important discovery, he had the units of frequency named after him.
Okay, so I think we established this earlier that, that the pitch of a note is directly related to the frequency that, that the wave is vibrating at. So this is just a chart of scientific pitch notation. As you can see, lower frequencies emit lower notes and higher frequencies emit higher notes. So to understand this chart, you need to learn a little something about musical theory. If my beautiful assistant will help me out here and play a chromatic scale consisting of A, A sharp, B, C, C sharp, E, D sharp, E, F, F sharp, G, G sharp, then A an octave higher. So as you can see, each one of these notes corresponds to a frequency that's emitted, but you can also see that there are multiple notes of the same kind, and that's a little bit about octaves, if my assistant will help me out again. You play a middle C.
Sure. Right there.
Beautiful. Okay. Middle C, right here, it can be shown to be vibrating at 261.63 hertz. And if he plays an octave down, that is 138 and 81/100ths of a hertz. It can be seen that one octave down of the of one octave down on the C is exactly at half the frequency of the one above it, and vice versa, as going up an octave for middle C is twice as much as that. This is the original one.
So what we did was we measured the distance from the bridge of the guitar up to each individual fret. So from the bridge to the first fret here is 8.0625 inches, and that is a frequency of 261.63 hertz. We continue this process all the way up to the last fret here, so 23.9375 inches away from the bridge, which had a frequency of 87.307 hertz.
Okay. Now we took that table and we put that into Microsoft Excel, and we kind of graphed that out, and we also came up with a line of best fit, which is this function up here, which we call f of x. And basically for us, this is the equivalent of like a position function, whereas you plug in any inch, any distance on the fretboard that you're playing the note and that's vibrating, is the result of the function would be however many hertz that is emitting and whatever note that would correspond to. So like as an example, if we chose like
9.
okay, so we chose 9 inches, somewhere around here that we want to play on our low E string, because that's what we use. we would plug in 9 to that function, and I really don't want to do that in my head, so
Me either.
yeah, so
There it is.
Yeah, magically we get 233 and 8/100 hertz, and that corresponds most closely to an A sharp, and I think that's mostly an A sharp 2. So you know where an A sharp 2 is.
You go right ahead.
I think. Sounds about right. That sounds pretty spot on. So, yeah. So that's our position function.
So next to the position function, we took the derivative of it, and this gave us a velocity function of sorts. It's kind of interesting because there is no time unit, there's no seconds or minutes or anything like that, we just have per inch. And so our velocity function essentially shows us that as we go farther and farther out, so if this string were to go on forever, your change would be less and less as you increased an inch. So as you would go farther and farther, for every inch, your change would be essentially, not 0, but it would be essentially 0. The limit would approach 0. And as you would get smaller and smaller, as you go to an infinitely small number here, your change would be greater and greater in the negative direction per each inch that you change.
All right, and then of course we had to take the second derivative when second derivative of a position function is like an acceleration. So this is our acceleration of hertz per inch. So it would hertz per inch as we can see there. And so basically what we're saying is for every ferret that we or fret that we go
Right.
every measured in inches that at that point the rate of change of the hertz per inch is changing that much greater, and you can see as we get closer to the bridge down here and smaller values that it is changing that much quicker. But hypothetically, if these strings went on forever, it approaches 0. So at that point, it wouldn't be at 0, but it's very close to almost no change whatsoever. But it's kind of cool because if you exponentially get it larger, it'll not. How am I gonna say this? It'll never be the same note. It'll always change the slightest amount. So yeah.
Next we have a picture of our ferret board. I mean, ferret, whatever these little metal things are called there. And that brings us into the history of calculus a little bit. So calculus was created in the 17th century by Isaac Newton and Gottfried Leibniz. Newton's use of calculus was more physical and tangible, so like real life applications, as where Leibniz's application was based more on changes in graphs and analytical math. As people have said before, there's a long ongoing dispute over who actually invented calculus, but due to the fact that they both made very important contributions, we like to just give them both credit. And this brings us into the race course paradox. So there's this thing where if you have a certain distance to go, and you can go ahead and click the next slide there, if you were to run halfway, you'd be halfway there, and if you were to run another half, you'd be a quarter of the way, followed by an eighth, a 16th, 32nd, 64th, and so on and so forth from there. And this is an infinite series, which we haven't gotten much into in Calculus AB, but it is a calculus thing. And with infinite series, it just goes on forever, and you can continually get closer and closer, but you'll only be half of what you were before. And so...
And this is directly related to the fretboard, like how we said earlier that an octave up is twice the frequency. There's also a law out there, was it Mercine's
Yes.
laws on strings. And his first law basically said that if the length of a vibrating string is cut in half, the frequency is doubled, and that's an octave up. So we can take this concept and go halfway each time, and we should be able to reach infinity.
Right.
Well, not reach.
Infinitely many.
Infinitely many. So there and about halfway.
There's an E.
There's an E.
There's an E. There's an E. And that's probably right over 23,000 hertz, so we probably can't hear that one exactly anymore. But there's an E there.
Yeah, but what's cool about this is we can say that since this is an E string and there are the chromatic scale, every note is on here, we can say that there are an infinite amount of every single note on just this one string. Now we might not be able to hear it because we can't hear above 23,000 hertz.
Right.
So, but it's a fact that there are an infinite number of E's on that string.
That is our presentation.
We also have other applications that we don't want to miss out because that's part of our grade.
That's true. Last I checked.
Yeah, but you know, I think we used a lot of derivatives, and
Yeah.
we found out recently, very cool, that you can use a derivative to find the average velocity of like a track runner. We can also like find the rate of a melting cone.
That'd be cool.
I think that would be really
Yeah, you
cool.
could do like the related rates of water and fish tank. So that'd be.
Oh yeah, that would be cool.
That'd be
Related
interesting.
rates
Or
there.
like optimum angle for a soccer goal, like you could create a program out of just ridiculous language that makes optimum angles for soccer goals with
Using derivatives, I
Right.
like it. And then what is leaping and dancing?
Leaping and dancing, you know, you just gotta get the little bit of a maximum height. You gotta go for the maximum
Yeah,
height.
I definitely saw maximum derivatives.
Right, there it
Yeah.
is. And airplanes too, you gotta calculate your maximum profit, how far you're gonna travel in your flight, there's all sorts of things. Like you can even do like discus, like the area under a curve of a discus or something.
All right. Well, that's our
Infinite percentage.
presentation. So, yeah.